All right, so we're going to go ahead and continue our discussion on stoichiometry. So stoichiometry is the process, very simply, is the process of converting the moles of one thing, okay, to the moles of another thing. But to be able to do that, you have to have a balanced chemical equation. Do that. Okay, so something like this. So you have a balanced chemical equation. It has coefficients, and you want to convert the moles of A to the moles of B. So very simply, whatever amount of A you're starting with, 0.897 moles of A, I can convert that to moles of B using, from the moles of A, using the balanced chemical equation. So here there's 1 mole of A for every 2 moles of B. 2 moles of B for every 1 mole of A. And that would be the conversion. Okay? That's stoichiometry. Stoichiometry is simply the process of converting one compound to another compound using a balanced chemical equation. But it has to be in moles, because the balance of the equation here isn't in grams. It's not 1 gram of A and 2 grams of B. It's 1 mole of A and 2 moles of B. So that's how I would set up my conversion, in moles. Okay? So for example, here's a question. How many grams of lithium are needed to produce 9.89 grams of hydrogen, according to this chemical equation? Okay? So here we have lithium. It's reacting with water. It's going to boil and produce lithium hydroxide and hydrogen gas when you put it in the water. Okay? So if I want to produce 9.89 grams of hydrogen, so 9.89 grams of hydrogen, how much lithium is needed in grams? So this is a very practical question, because in the laboratory, we would want to know how many grams of lithium to take, put it in water, and then we would have a certain idea of how much hydrogen we are going to produce. We're going to produce 9.89 grams of hydrogen. Okay? So, can I convert the grams of lithium? The grams of hydrogen. Can I take the 9.89 grams of hydrogen and convert it directly to the grams of lithium in one step? No, I cannot, right? Why not? Because these coefficients are not in grams, right? They're in what? Moles. So in order to do this, I'm going to have to do more than one step. The only time I would ever do one step is if it's in moles to moles. Whenever grams are involved, that's an indication that it's going to be more than one step. Okay? So, what is the first step? Grams of hydrogen. 9.89 grams of hydrogen. And I'm going to convert it to what? Moles of hydrogen. Now that it's in the moles of hydrogen, I can do what?
You can convert to the moles of lithium.
That's right. Now I can go to the other thing. I can go from hydrogen to lithium. But I can only do that when it's in moles. That's why I had to do the moles. This conversion right here is not part of stoichiometry. The stoichiometry is going from one thing to another thing. And that's what I'm going to do right now. moles of H2 to the moles of lithium. Okay? Have I answered the question now that I'm in the moles of lithium? So what's the last step? Now I need to go to the grams of lithium. Okay? So this will be my process. This is the process that I'm going to follow. Okay? So when I want to figure out what units go down here, I simply have to look at what came before it. And I drop my units. Drop, drop, drop. So what units go right here? What units go right here? And then the last. Okay. Now I have identified all the conversion factors that I will be using in this conversion. Grams to moles of hydrogen, moles to moles between hydrogen and lithium, grams to moles of lithium. Those are the conversion factors. Whenever I have a gram to mole conversion, the moles are always what?
1.
They are always 1. This is a big point of confusion. A lot of people look here and they see that there's a coefficient. Well, here it's not a big deal because the coefficient is 1 anyways. But let's take lithium. Right here, gram to mole conversion, moles are always 1. But you look here and you say, oh, but there's 2 lithiums. So you want to put a 2 there. That's not what we're trying to use. We're not trying to figure out how many grams of lithium there are in 2 moles. We want to find out how much lithium weighs for every 1 mole. That's what we want to put here, not every 2. That 2 is going to come and play right here anyways. Okay? So, grams of moles, moles are always 1. Whenever it's grams, where do I find it? The periodic table. 6.941 grams of lithium for every 1 mole of it. Get rid of this thing because it's kind of confusing. Okay? Now, grams of hydrogen. Well, there's 2 of them. H2. 2. Okay? Now, whenever I have a mole-to-mole relationship, stoichiometric relationship, where does that come from? The coefficients of the balanced chemical equation. So, lithium has a coefficient of 2, so that's what I'm going to put here. Hydrogen has a coefficient of 1, so that's what I'm going to put right here. Okay? 9.89 grams of H2 times 2 times 9.641 divided by 2, that's how I'm going to find my answer. That's how I'm going to set up this stoichiometric conversion. Okay?
The coefficient for 1 that's H2 1.
This has a coefficient of 1. It doesn't have to be represented, and there's no coefficient, that means 1.
Yeah, just like that. No, just okay. I was looking at the one that was,
Looking at what? I'm sorry?
I was looking on the other half.
Over here?
Yeah.
Oh, that's for water. So that's water. Hydrogen, right there, all by itself. That's what we're looking for. Okay, so that's the process of how I'm going to set up these conversions. What is the mass of zinc chloride formed if 128.2 grams of zinc reacts with excess HCl? What does this mean? Okay? Yeah, it means that there was some left over during the reaction. It did not go to, the HCl did not get all used up. It's an excess. There's more than enough of it. So will the HCl be a part of this conversion? Do I include it? No. All that means is that it's not part of determining the outcome. What determines the outcome is the thing that runs out. 128.2 grams of zinc is going to go to 0. All of it will be used. And when all of it is gone, the reaction will stop. And when the reaction stops, I stop producing product. Therefore, it's the zinc that determines how much product I make, not the HCl, because the HCl is in excess. So I do not include it in my conversion. It's not part of it. Okay? So we're taking zinc plus HCl, and it's going to produce zinc chloride plus hydrogen gas. Okay? So, what is the first thing I need to do to this equation? I need to balance it, right? Because it is not balanced. Okay, so we have a balanced chemical equation. Now that I have a balanced chemical equation, I can do the stoichiometry because I know the stoichiometric relationships. Okay? So, I'm going to start with 128.2 grams of zinc, and I'm going to convert it to grams. Whenever it says mass, that always means grams of zinc chloride. Okay? So go ahead. I want you to set it up. Set it up. Show me the process that you would follow. Don't worry about calculating it. It's more important right now that you know how to set up the process. How are you going to set it up?
For the grams of zinc chloride, do we just add them to like periodic table?
Yes. Okay, so I'm starting with the grams of zinc. But I cannot convert it from zinc to zinc chloride unless it's in what units? Moles. So before I can do the stoichiometry, my very first step is I have to convert it to moles of zinc. Moles of zinc. I'm sure you meant the right thing, but it was okay. Okay, grams of zinc to the moles of zinc, because now that it's in moles of zinc, now I can change it to something else, which I need to, because this, I'm going from zinc to zinc chloride. I can only change it if it's in moles. Okay? So now that it's in the moles of zinc, now I can change it to zinc chloride. Moles of zinc chloride. But that doesn't answer the question. Although the stoichiometry is finished, I'm done doing the stoichiometry, it doesn't answer the question, because the question wants me to find the mass of zinc chloride. Mass is grams. So my last step, grams of zinc chloride. Okay? Drop my units. Grams of zinc, moles of zinc, moles of zinc chloride. And now I have everything, all my units filled out. The dimensional analysis is finished. All my units cancel except for grams of zinc chloride. Okay? Zinc. And now I just have to fill it in. Grams and moles. Moles are always 1. Grams, where do I find it? Periodic table. 65.38. Whenever I have the mole-to-mole relationship, that's the stoichiometric relationship. Where does it come from? The coefficients of the balanced chemical equation. What are they for these two? Just 1 and 1. Exactly. Okay? The 1 mole of zinc for every 1 mole of zinc chloride produced. Moles of zinc chloride in the gram to mole conversion, moles will be 1. Grams of zinc chloride. Somebody find that? What is it? 70 plus 63.
6.296.
Okay? So 136.296. That's the setup. Okay? That's how I would do it. And then I would take this 128.2 times 136.29 divided by 65.38. Okay? Who found an answer for that?
267.38.
Okay. So this is called a theoretical yield. That's called a theoretical yield because I didn't actually go do that. I just calculated it. So it is just theoretically how much I should make. If I have 128.2 grams of zinc with more than enough hydrochloric acid, more than enough, then I will theoretically produce 267.38 grams of zinc chloride. Now in reality, are you going to produce that exact amount? Probably not. Maybe something wasn't as efficient in your reaction as it should have been, or the human error of some sort, and your reaction, you lose product in one place or another, and you actually get 254 grams. Okay? That would be an actual yield. This is a theoretical yield. Okay? The theoretical yields are the calculated amounts. Okay? That's a P4. Okay, how many grams of phosphorus are needed to produce 290.0 grams of tetraphosphorus decaoxide? Okay? So, we'll get a balanced chemical equation. Let's make it more interesting. So like this. Okay? Which that's not really how it would be. But let's just go ahead and take it like that. Okay? How many grams of phosphorus are needed to produce 290 grams of tetraphosphorus decaoxide? Okay, so you're going to start with your 290.0 grams of tetraphosphorus decaoxide. Okay, and you want to convert that to the grams of phosphorus. So you're starting right here, 290.0, and you're going to go here to grams of phosphorus. How many grams of phosphorus are needed? Okay. So let's go ahead and look at this. So we have 290 grams of tetraphosphorus decaoxide, and I want to convert that first step to what? Moles of tetraphosphorus decaoxide. Okay? Now that it's in the moles, I can convert it to the other thing, which is simply just the moles of phosphorus. Okay? That's the stoichiometry. This is not stoichiometry. That's just a simple conversion so that I can do the stoichiometry. Okay? Then I can to answer the question, I have to convert it back to grams of phosphorus. Okay? So, this is where I'm at. Now I simply drop my units, grams of tetraphosphorus decaoxide, moles of tetraphosphorus decaoxide, and then the moles of phosphorus. Grams and moles. Moles are always 1. I want to know how many grams there are in 1 mole of tetraphosphorus decaoxide. What is it? Who figured that out?
282.896.
Okay? Now, this is a stoichiometric relationship. The balanced chemical equation tells me the relationship between moles of phosphorus to the moles of tetraphosphorus decaoxide. How many of these will produce how many of these? Okay? That's what we're looking at. So 1 tetraphosphorus decaoxide is produced from every 4 moles of phosphorus. Okay? That's what the coefficients are doing for me. They're telling me the relationship. Now, grams and moles. Moles are always 1. How many grams are in 1 mole of phosphorus? What was it? 31? We'll just say 30.9. You can put 30.97367 if you want. Okay, 31. All right, so what is our theoretical yield then? How many grams of phosphorus theoretically would need to react with excess oxygen, essentially, to produce 290 grams of P4O10?
126.62.
Okay, 126.62 grams of phosphorus. Yes?
Like the test and like the homeworks, you're just looking for the value that's close to, like, with rounding and stuff. You're not like, I got a little different one than that. That's
Yes.
still the same?
Yes.
Okay.
Yes.
For the last one, I got I put 4 in the bottom and then multiplied.
Right here? And you multiplied 31 times 4?
I did phosphorus times 4 since it's horrible, and I got that gram, and I started the same answer.
Yes, because technically you're finding the grams of phosphorus for 4 moles of phosphorus, which technically is the same thing as 31 for every 1. So the ratio is the same. It's just that that's not really, I don't want you to get confused by that. That would work every time if you were consistently doing it, okay? But this 4-to-1 ratio, that's where the 4 comes into play. You don't have to repeat it, okay? And then multiply by 4 again, all right? So as long as this ratio is the same, yes, you'll get the same answer, but that's an extra step that's unnecessary. You don't really need to do, okay? So that's why we want to find the mass for every 1 mole, or here the mass for every 1 mole as well, because that's the conversion factor, that's the ratio. And here is where these coefficients come into play. That's where we'll use them. Okay, any other questions? Iron 3 oxide can be formed when iron reacts with oxygen gas. Calculate the mass of iron 3 oxide formed when 26.25 grams of iron reacts with excess oxygen. Okay, so go ahead, try to set that up. Fe. Iron is Fe. Yeah, that's right. Now, one note I'm going to make is, in what form will you find oxygen? O2. That's going to change your balance. So make sure you're using O2, not O.
The 3 is in charge, correct?
The charge of iron is 3 plus, not, doesn't mean you have iron 3 doesn't mean you have 3 irons in your formula. It means that's the charge of the iron. Fe 3 plus and O2 minus. What's the formula? Calculate the mass of iron, 3 oxygen. Now let me just make one comment. So this has a 3 plus charge, and the oxygen is 2 minus. So we would say O2 is under 6. So we can break oxygen up. We can't break it. Here it is. That's not O2. So it's not O2 3. We'll figure out exactly how it's on. So this is how you would get that. The oxygen's in excess, so it's not part of it.
Oh, so that's it. That's what
26.25 grams of iron, and you're trying to find iron for 3 ounces. So you just have, everything's right if I was going from here to here, but I'm actually going from iron, instead of iron.
Oh, I just did it wrong.
But everything is,
Oh, wait.
all the numbers are, everything's okay. Okay, so you did a great job if we're going that way, but yeah. I think that math is a little long, but otherwise, yeah, good.
So this whenever you find the grams of iron and then add it to the solution.
Yes, so Fe2.2, and then oxygen 3, and then this gives you 6 oxygen.
So you just want to find this here.
So, yeah, find the balance.
No,
So this is grams of I thought this was grams of
I think that is maybe how many.
And multiply that by 2.
That's the 2F. I put in 203. Yeah, I just put
And that's the balance.
2F.
So you want, this is, so first we gotta, that's O2, negative 2 minus 4.
I lost it.
So oxygen's minus 2.
Yeah, but he said that electrons.
So then the formula is O2, O3. Okay, so this one made you work a little more. All right, but I think you guys are getting there. So 26.25 grams of Fe. So we have to have our balanced chemical equation, right? So Fe plus O2 produces Fe2O3. So if I balance my irons, I need 1.5 oxygens. Go. Okay. To get a balanced chemical equation, then I multiply everything by 2. This becomes 4, 3, and 2. Okay, that's my balanced chemical equation. I'm going to use that to calculate this. I'm going to go from the grams of iron to the moles of iron, then to the moles of the other thing, which is iron 3 oxide. So Fe2O3. And then to the grams of Fe2O3. I drop my units, grams of Fe, moles of Fe, moles of Fe2O3. I have, for every 1 mole of iron, it is 55.847 grams. The mole-to-mole relationship here, the stoichiometric mole-to-mole relationship is for every 4 irons, I have 2 iron 3 oxides. For every 1 mole of iron 3 oxide, it weighs 160 grams. Okay? Or 159 something, whatever you guys found, right? Approximately 160. Okay. So, that's how I'm going to do this. This times 2 times 160 divided by 55.847 divided by 4. Okay? Because those are the stoichiometric relationships. All right. That's how I'll calculate that. So my theoretical yield here is what?
37.53.
So theoretically, from 26.25 grams of iron, I would produce, 37.53 grams of iron 3 oxide. Okay? That's a theoretical yield. That is not my actual yield, just a theoretical yield. Okay, so here's the glucose plus oxygen. This is cellular respiration reaction, essentially, or just combustion of glucose. Produces carbon dioxide and water. If 856 grams of glucose is consumed by a person over a certain period, what is the mass of carbon dioxide produced? Okay, so this is through cellular respiration. It's going to break down in our bodies. And if I ingest 856 grams of glucose, what is the mass of carbon dioxide that I will produce? Okay, so we're going from 856 grams, and it's a balanced chemical equation. How nice, right? Okay, you have your balanced chemical equation. You're starting with 856 grams of glucose, and you want to find out how much carbon dioxide is produced. So 856 grams of glucose, and we want to go to the moles of glucose, to the moles of the other thing, which is carbon dioxide. That's the stoichiometry step, to the grams of carbon dioxide. And that will be the process that I would follow to do that, to answer that question. Okay? All right, now, the theoretical yield is a calculated amount. The actual yield is the amount that you would actually collect after running a reaction in the laboratory. So I run it in the laboratory, I weigh the product, and that's my actual yield. Okay? So, to determine how well you did on your reaction, you can set up a percent yield. A percent yield tells you how well or how closely you got to the actual theoretical yield. Okay? So this can be helpful, because if you get an 80% yield, then you could probably say, oh, I might need to improve that. If you get a 98% yield, you're like, hey, that's an awesome reaction. It's very efficient. I'm doing a good job. Okay? So, percent yield is calculated by taking the actual yield that you obtain, which, since we're not in the laboratory, if you are in the laboratory, then you would actually find it. But because we're not, it would always be told to you. You would always be given that in the question. You actually made this amount. You collected this amount. Okay? That's your actual yield. That would always be given in the question. Theoretical yield, not always, because you can do what to get it? You can calculate it. Okay? This is your reaction. How much should you make? That's your theoretical yield. So you would always be given this, but not always this, because you can calculate that. Okay? So percent yield, actual over theoretical times 100. It's a very straightforward equation. It'll be on your reference material. You just simply need to take the actual over theoretical times 100. Okay? So when we're calculating a theoretical yield, there is one thing that we have to take into consideration. That is a limiting reagent. Okay? So let's take the water equation. Produces 2 waters. Okay? So if I told you you had 5 grams of hydrogen gas, and I asked you to tell me how much water in grams you would produce, that'd be pretty straightforward, right? You set up your equation, grams to moles of hydrogen, then to the moles of water, then to the grams of water. Okay? But what if I said you had 5 grams of hydrogen and you have 15 grams of oxygen? How much water do you produce? So do you see how this is a whole different type of question? I have 2 things to start with. One of them will tell me the amount of water I produced. It's either this one or it's this one. Because one of these is the limiting reagent. One of them is going to run out, and when it does, the reaction will stop, and the other one will be in excess. There will be some of it left over. So I cannot calculate the final yield from the thing that's in excess. Can you tell me which one of these is the limiting reagent?
Oxygen.
Okay, why do you choose oxygen?
Because there's less moles.
Less moles. Okay, that's a good reasoning. Okay, less moles is a pretty good reasoning. But then you also have to consider the coefficients here because of moles. Okay, I cannot just look at this and determine which one is limiting. It's not obvious to me because this is in grams. A gram of hydrogen is 1 gram. Hydrogen is 2 grams. I have 5 grams of it. That means I have quite a number of moles of it compared to this is how many grams? 32 grams. Do I even have an entire mole of oxygen here? I don't. So do you see? I cannot just look at this and just say, oh, I know which one's limiting. Okay? I need to calculate it. Well, how will I calculate a limiting reagent? You compare one of them to the other one. That will tell you which one is limiting. So, for example, I say 5 grams of H2 to the moles of H2 to the moles of O2. So the question here is, if I have 5 grams of hydrogen, how many grams of oxygen are needed to react with it? And this is going to tell me whether it is a limiting reagent or not. Okay? So from the moles of H2 to the moles of O2 to the grams of O2. Grams of H2 moles of H2, moles of O2. Oops. Okay, so who has their calculator out? 5 times 32 divided by 4, what is that? What is it? 40? 40 grams of O2. If I have 5 grams of H2, how much O2 will react with it? 40 grams. Am I anywhere close to 40 grams? Not anywhere close to it, right? So what does that tell me about hydrogen? Is it going to be an excess, or is it going to be the limiting reagent? Excess. Okay? Because I would need 40 grams of oxygen to make a perfect reaction with 5 grams of hydrogen. Okay? I don't have that much oxygen, so that means my oxygen is limiting. It's going to run out first. The hydrogen is going to be in excess. So, which one of these, hydrogen or oxygen, is going to determine the amount of water produced? Oxygen, because it is the limiting reagent. The limiting reagent determines the outcome. If I did it for hydrogen, the hydrogen would give me a number above the amount that I would actually produce because it is in excess. So I need to figure it out not using hydrogen, but using oxygen. That's why I need to know which one is limiting, so that I can determine my theoretical yield. So let's look at if you had started with oxygen instead of hydrogen. How would it look? 15 grams of O2 to the moles of O2 to the moles of H2. So let's compare O2 to H2 to the grams of H2. Grams of O2, moles of O2, moles of H2. Okay? So here, I want to figure out whether oxygen is limiting or not by comparing it to H2. So 32 for 1. I have 2 hydrogens for every 1 oxygen, and I have a mass of 2 for every 1 mole in hydrogen. 15 times 4 divided by 32. What is it? 1 point what? I would only need 1.875 grams of hydrogen to react with 15 grams of oxygen. Okay? So, do I have more or less than 1.87 grams of hydrogen? I have a lot more than that, right? So right there, once again, this is verifying that the hydrogen is excess. Therefore, the oxygen would be the limiting reagent. Okay? This is how we're comparing one thing to another thing to determine which thing is limiting. Why do we do that? So we can determine the theoretical yield. How much would we produce? So, I haven't answered the question. If the question is, how much water do you produce? I haven't even answered that yet because all I've done so far is answered which one is limiting. So my final equation to answer the question would have to start with the 15 grams of O2 because that's the limiting reagent. Excuse me. That's the limiting reagent. Grams of O2 to the moles of O2 to the moles of H2O to the grams of H2O. Grams of O2, moles of O2, moles of H2O. Grams of moles, moles are 1, grams are 32. There's 32 grams in every 1 mole of oxygen. Mole to mole, I find from the chemical equation, there's 2 moles of water for every 1 mole of oxygen according to my balanced chemical equation. grams to moles. Moles are 1. There are 18 grams of water in every 1 mole of water. 15 times 2 times 18 divided by 32. What's my answer? 16.875. 16.875 grams of H2O. Oh, look at that. That's interesting. 15 grams of oxygen plus 1.875 grams of hydrogen gives me 6.875 grams of water. Amazing. Okay? All right. So this is my theoretical yield. What if I had used the wrong reagent? What if I had used hydrogen? 5 grams of H2. Excuse me. Moles of H2 to the moles of H2O to the grams of H2O. Okay, 1 mole has 2 grams for H2. It's a 2 to 2 relationship according to the balanced chemical equation. There's 18 grams of water in every 1 mole of it. Okay, what is it? What is this? 45? 45 grams of water. So do you see how this number is absorbent? It's too big. That's the wrong answer. This is the right answer because it comes from the limiting reagent. So you don't have to, but if you wanted to, you could always do it for both of your reagents. Find out which one is the least number. That would always be your limiting. Okay, that could be a check for you. Did I do it right? Did I choose the right one? Whichever one is the least, gives me the least product, that's the limiting reagent. Okay? All right. So you find your limiting reagent, and that's the one you use to answer the question. Yes?
So you're saying whichever, when you compare them, whichever comes out to the least amount is yours?
If you do it this way. If I started with 15 grams of oxygen and went to water, and then started with 5 grams of hydrogen and went to water, you can see my limiting reagent is in the least amount. Because the one that would be in excess would always give me a larger amount. The limiting one would always give me a smaller amount of product. Okay? So I could verify that this that the oxygen was my limiting reagent because it gives me less product than the hydrogen gives me. Okay? All right. Let's look at this figure. Okay? So to make a sandwich, okay, we need 1 sandwich equals 2 slices of bread and 1 slice of cheese. I guess this is a cheese sandwich. Okay? Not my very favorite sandwich, but okay. So we have 28 slices of bread here and only 11 slices of cheese. Right? So what's in excess? The bread. We have more bread than we need. So it's in excess. So I cannot make half of 28. I can't make that many sandwiches. But I can make 11 sandwiches because I have 11 slices of cheese, and it's the limiting reagent. Okay? So that's kind of the same idea for what we're talking about with these moles, or how many moles we start out with something and how much is it going to produce. Okay? Here's another example. This is my recipe. 2 cups of flour, 2 tablespoons of baking powder, 2 eggs, and 2 cups of milk to make 12 pancakes. How many pancakes can you make with 4 cups of flour, 6 tablespoons of baking powder, and 6 eggs, 6 cups of milk? You can make 24, right? Even though I tripled these, right, I only doubled this one. Therefore, this is my limiting reagent. It's my limiting ingredient. It's the thing that will determine how much is produced. Okay? It's the same idea with this chemistry, stoichiometry stuff that we're doing. Whatever thing is in the least amount, not in gram amounts, but in the whichever thing runs out first in the reaction will determine how much product you can make. Okay? Okay, so we have zinc plus sulfide gives me zinc sulfide. If 50.0 grams of zinc is reacted with 20 grams of sulfur, determine the limiting reagent. Okay, so figure out which one's limiting. Okay, so is this what you guys did? Anybody do this one? Okay, so what is this telling me? Sulfur is what?
The limiting.
Sulfur is limiting. Oxygen is in excess. Okay, good question. So this is how much sulfur would react with this amount of zinc. Do I have that much sulfur? No. So I don't have enough sulfur to react with all of this. So that means the sulfur is limiting. Okay? So the sulfur is limiting. Did anybody do it the other way, starting with sulfur? Okay, what did you guys find? 40.87 grams of zinc. Okay, so let's look at it like that. 40.87 grams of zinc would, and I have 50. So that means zinc is in excess because I only need 40.87 grams of it. So once again, we have identified zinc to be excess, sulfur to be the limiting reagent. Okay? All right, guys, we'll see you next time. We'll finish this up in the next class.